Visual or apparent magnitude, M, is a measure of the brightness of a star or other astronomical object. An object's apparent magnitude depends on its intrinsic luminosity, given by what's burning in the oven. Fusion: the heavier the elements, like the carbon-oxygen-nitrogen fusion chain, its distance from us, and any extinction of the object's light caused by interstellar dust along the line of sight to the observer, a blocker, tiny little things. Nevertheless, they travel faster than a bullet, so they can pierce anything, even steel. Don't mess with them, unless you have adamantium. The magnitude scale was introduced by the Greek Hipparchus before the ancient Roman astronomer Claudius Ptolemy, whose star catalogue popularized the system by listing stars from first magnitude, brightest, to sixth magnitude, dimmest. The modern scale was mathematically defined in a way to closely match this historical system. The scale is reverse logarithmic. The brighter an object is, the lower its magnitude number. A difference of 1 point in magnitude corresponds to a brightness ratio of the fifth root for the number 100, or about 2.512, then multiplied to their corresponding flux logarithmic dividend. Flux is the power released from the star measured in watt per square meter, just like that light bulb you just bought. For example, a star of magnitude 2.0 is 2.512 times as bright as a star of magnitude 3.0, 6.31 times as bright as a star of magnitude 4.0, and 100 times as bright as one of magnitude 7.0. The brightest astronomical objects have negative apparent magnitudes, for example, Venus at -4.2 or Sirius at -1.46. The faintest stars visible with the naked eye on the darkest night have apparent magnitudes of about +6.5, though this varies depending on a person's eyesight and with altitude and atmospheric conditions. The apparent magnitudes of known objects range from the Sun at -26.832, to objects in Deep Hubble Space Telescope images of magnitude +31.5. The measurement of apparent magnitude is called photometrics. Photometric measurements are made in the ultraviolet, visible, or infrared wavelength bands using standard passband filters belonging to photometric systems such as the UBV system or the Strömgren-UBI circumflex squared system. Measurement in the V-band may be referred to as the apparent visual magnitude. Apparent magnitude is really a measure of illuminance, which could also be measured in photometric units such as lux. These measurements are of vital importance, especially that of a Type 1a supernova, which happens when in a binary gravitatory stellar system, made by a giant star and a companion white dwarf, a giant diamond, this latter pulling in by the power of gravity, stellar mass from the giant star forming a disk of hot gas, reaches a critical point of neutron absorption in the inner region of the disk, causing a cataclysmic release of energy in a shock wave we call supernova. As the critical point should be the same anywhere in the universe, the lux should always be the same too. So basically their lux tells us their distances. As they are farther away from us they look dimmer, but with the same power output. This helps us to create and set better lenses and sensors for telescopes in every electromagnetic frequency, to study naturally how elements form, and those processes, to better understand their physical and chemical properties. Interesting, isn't it? I'm having my own space program, you'll see.